All right, yeah, we'll solve the fourth question from the exam. So the fourth question is about the FSMs, the finite state machines. So in this question, you are basically given a state representation of FSM. And the question asks like several questions related to the FSM, for example, the representing it in a Boolean equation in one-hot encoding, binary encoding, and output encoding, and as well as like what's wrong with this representation, and we're going to try to correct it. So you can see it, right? Okay. So for the question, we have states, and for the states, we also have the output, and these are the TAs and TBs are inputs. So the question asks, so there's a critical component missing in the FSM, and what is this missing component? So if you look closely to that FSM, you'll see that there is no reset line, right? So we need to have that in order to have basically have a deterministic behavior in that FSM. So we'll say that we don't have the reset line for this FSM. So for the second question, it says, of the two FSM types, which are Moores and Maileys, what type of an FSM is this? Basically, if you look at that representation, you'll see that the output, it only depends on the state, but doesn't depend on the input, right? So this means that this is a Moore's representation. So if the output only depends on the state, then this means that this is Moore's. So all right, so far so good, I guess. These are the relatively the easier ones. All right. So for the C, it says that list one major advantage of each type of state encoding below. For one-hot encoding, our aim is to reduce the next logic wires, right? So for the one-hot, we basically try to represent each next state logic, hopefully ideally with single bit. So this means that you reduce next state logic. With the one-hot encoding. So for the binary encoding, our aim is to use the least amount of bits to represent the states. Yeah.
My question about the reset signal, because the book explicitly states that it's optional.
For the fourth one, for this one. So I'm actually not sure about this, but like. So does it say the same thing in the slides as well, or?
I don't know what it says in the slides, but in the book it says it has optionally a reset signal.
Okay. So should we comply with that, Juan? If the book says this is optional to have the reset line, do you think like this is a missing component as well, like a critical component? So if the book says this is optional, I will say yeah, then okay. I think for that one, yeah, we can comply with the book, but Giray has a point, I guess.
Maybe it's better if you send that part of the chapter in the book on Moodle.
Okay.
We can
Yeah.
also read that and
Yeah, that's true. Yeah, thanks for that. Yeah.
Could you also see that there is no, because I think, I'm not 100% sure, but I think in the book it says not, the reset line is not necessarily that you need an initial state. Is that what may be missing?
Yes, with the reset line, we basically define the initial state. Yeah.
Okay, so reset line implies initial state.
Yes, this is true.
But couldn't we also just have an initial state without a reset line?
I will doubt so actually. So so for the representation, yeah, you can say that, yeah, this is our initial state, but to really have it as an initial state, then you should make sure that when you start this FSM, it's really gonna be the initial state, right? So how do you ensure that? You need to have some sort of reset line so that it goes there when you reset, and then you start it as an initial state for that. So basically, it means the same thing, to have the initial state and the reset line. Okay. Any questions related to those? Okay. So for the binary encoding, yeah, as I said, we try to basically use the least amount of bits to represent the state. So this means that you reduce the flip-flops that you need to represent the states. So this is, I would say, the major advantage of binary encoding. Reduce flip-flops. And for the output encoding, our goal is to basically use the least amount of logic units to encode the output, right? So this is also clear. I guess, if there's no question with those. Okay. So starting from the question ask us like, so okay, we are given those states, and like, so how should we write basically the Boolean equation of that state? And we have three options. One option is one hat encoding, and second option binary, as you can see here, and then the third option is output encoding. So for all of those, what changes is basically the way that we represent the states, and the rest won't change, right? So, and basically, so what I'm gonna do now is I'm gonna write a truth table, kind of like a higher level truth table, I will say, because I'm not gonna represent the states with the bits, and this will be my kind of like a reference for the next three questions. So, for that truth table, I have current state, let's say. I have my TA, TB, the output is 2 bits, so O1, O0, and the next state, right? So for the current state, starting from the A, let's say, so if I have, so the TA basically don't care. So if I have TB1, I'll visit C. For again being in state C, A, TA don't care. And if I have TB not, I'm sorry, yeah, that's, so if I have 0 here, so I'll visit B. So if I have 1 here, I'll visit C. And the output when I'm in state A will be 1, 0, 1, 0. So for the state B, so if I have 0 for TA, then I'll visit C. Then this means that 0 and don't care for TB. C, right? Yeah, C. So for again B, if I have TA1, don't care for TB, then I'll visit A. And the output will be 1, 1. For C, so no matter what, I'll visit D, then these TAs and TBs are don't cares, and the output will be the 0, 1, and the next state will be D. For D, so if I have 0 for TB and don't care for TA, then this means that I'll visit B, and if I have 1 for when I'm in D, then this means that I'll visit D again, and the output will be 0, 0, and 0, 0. So let me see if everything looks good here. TB0, I guess, yeah, will go to B, and TB1 will go to C, right? Okay. So this truth table is basically like a kind of like a higher level truth table here, I would say, because I don't have the bits for the current state and the next state, but I have the explicit bits for the output and the input bits, basically. So for the following three questions, basically, what I'm going to change, are only the current state, the way that I represent the current state and also the way I represent the next state. But those will not change, right? So these are basically independent from the encoding that I'm using. So I'm going to use these as a reference for the following questions. So I already written this, basically, if you wonder, to save some time. For the one encoding, so what I'm going to do, I'm going to try to represent each state using a single bit. Then this means that I'm going to write it like that. So for example, I can represent A with the least significant bit, and B as follows, C and D. All right. So here, then this means that every state is represented by a single bit. So I'm gonna put that into the table that I've written here. So I'm gonna represent the current state as C3, C2, C1, C0, and the next states as N3, N2, N1, and 0. And basically, so if you remember, so those two rows are AA. So I'm going to write the way that I represent A here, and which is this. And the next state was B, and I present B as follows. And again, A, because I have A here. And next state for this one will be C. And yeah, I think you kind of got the rest. So this will be B, and the next state will be C, and the way I represent C like this. And again B, and the output will be A. So this means that this. So I have C, and output, the next will be D. And for D, I have first B here, and again, I have D here. All right, so this is the truth table for D. Yeah.
First line shouldn't be solved because in the reference you wrote TAX, TB0, and then TAX, TB1.
Which one? I'm sorry.
The first two lines shouldn't they be solved in comparison to the reference list that you did?
Let me see.
If you compare the two lines, TA and TB, then on the reference list you have X0, X1, and
Oh yeah, you're right. So this will be 0, right? Yeah. And this will be 1, I guess. Yes, that's true. When TB is 0, yeah, I go to B, and then when TB is 1, I go to C. Yeah, that's true. That's correct. Okay. So based on that, basically, I'll write the next states and also the outputs, I guess, right? Yeah. C and B. Okay. All right. So let's write N3 here. So I'll check like when N3 is 1. N3 is 1 when for these two rows. And for the one-hot encoding, basically, this means that we ensure that if one of the bits in the input is 1, then this means that the rest should be 0. So we can regard them as don't cares. So when the entry is 1, this means that C2 is 1, and that's it, I guess. So let me do some sanity check here. Yeah. All right, so, and the second one is this, when N3 is 1 and C3, and also TB, I guess. All right, okay. So for N2, I have 2 rows as follows. So when N2 is 1, here I have C0, 1, and also TB as 1. Right? Yeah, that's correct. And again for N2 is 1, C1 is 1, and also TA is 0. So TA not. Let me check it again. Yeah, CA. Okay. So for N1, so I have here N1 1. So this means that C0 is 1, and so I have TB as 0. Okay. And for that one, I have C3 as 1, and also we have TB0. Right. So this should be simplified as, if I'm correct, yeah, TB C0 or C3, right? Okay. Yeah, for the next N0, I have 1 here, and that's it, I guess. Yeah. So this means that C1 1 and also TA 1, right? Yes. Okay. So these are the next state logic, the equations for the next states. And for the output, for output 1, I have 1 when basically, so I have the output 1 when basically either C0 is 1, and it also doesn't depend on the TA or TB, or when C1 is 1, right? Can you see that? The rest, so O1 is 1 when either C0 is 1 or C1 is 1, right? And for the C0 rows, then I have the TA already don't care, and TB also doesn't change the result. And it's the same as well for the TA. So I only have C0 and C1. For O0, I have ones here. So I have C1, 1, and it also doesn't depend on the TA, or I have C2, 1, and I guess that's also doesn't depend on the input, yeah. So these are the Boolean equation for output. Okay. All right, so we'll move on to the other one. So for the binary, so basically we can use 2 bits to represent four states, right? So basically I'm going to represent A then as 0, 0, but it's all up to you how you represent. It doesn't really matter. But like make sure that you use like minimum amount of bits to present the states. So the same thing that I've done like in the previous question. So but this time we have only 2 bits, then this means that I'll write it as follows. So 0, 0, and let me follow that one. Let me follow that one again. 0, 0, I have 0, 1, 0, 0, I have 1, 0, 0, 1, I have again 1, 0, 0, 1, I have 0, 0. For 1, 0, I have 1, 1. For 1, 1, I have 0, 1. And again, for 1, 1, I have 1, 1. So this will be the truth table for to represent states in a binary encoding. And so yeah, let's write the next state logic unit for N0. I'm going to write it here. For N0, I have 1 here, 4 here, So this means that C1 not, C0 not, and TB is 1. Okay. Or I have ones here. So notice that I always have C1 as 1, and when C0 is 0, I also I don't also depend on the TA, TB, or when C0 1, so it also doesn't depend on the either TA or TB. Okay, I guess that's the answer for that one. Let me check. Yeah. Yeah, and see. Yeah, then yeah, we can also simplify that, right? So this is always 1. For N1, I'll check the rows. I have 1 here, so this means that for this one I have C1 not and C0 not, TB not, C0 not, TB not, or C0 TA. Okay, and for these ones, or I have C1 as 1 and C0 not, or here C0 and TB, I guess. So this should, yeah, this is as is. Yeah, this is not simplified. For O1, so I have ones here. So this means that C1 is always 0. For that one, if I have C0 not, this also doesn't depend on the, yeah. I guess only C1 here. Yeah, only C1, but that's right. C0 not or C0. And for O0, so I have ones here again, and C1 will be 0 for 2 rows, and also C0 will be, let me write it in this way. And yeah, I actually have C0 not and C1 here, or C1 C0 not, right? So you can ignore that part. So this is basically XOR, right? So you can write it as C0 XOR C1 as well. All right, yeah. The question is a bit long, let's say, to write. But do you have any questions so far? How I write these truth tables? Yeah.
So if I don't simplify it, like if I don't write the XOR, is it really?
Yeah. So it matters for the last question because it's gonna restrict you saying that you only have and then I guess OR gates, right? So this means that you cannot use the XOR. Basically, you'll need to use the and then OR gates. But in this question, I guess, yeah, you can leave it as is because using minimum possible number of bits to represent the state. So, yeah, I guess you can leave it as is in that manner.
Because you have to see this is really a long exercise.
Yes, that's true. Yeah, yeah. But make sure that you also simplify it as much as possible. Yeah. Okay, so for the last one, that will be also, yeah, that's tricky because it asks for the output encoding. Then this means that I need to make sure that the output is encoded so that the output logic circuitry will be basically minimized, right? So how can I ensure beforehand without writing the truth table and the circuitry? So I'll show you basically how I did it in this question. So I have 2-bit outputs, and the inputs for the states I can use, let's say, 2 bits at least. So what I want to ensure is basically, I want to ensure that when O1 is 1, when O1 is 1, then O1 is determined exactly, hopefully, by 1 bit. Okay. So let's say that I'll use 2 bits for the states. Then this means that C1 and C0. So let's ensure that, for example, the output 1 is only determined by C1. Okay, and the output 0 is only determined by C0. So how can I then write the encoding in a correct manner so that I'll make sure that the output 1 only determined by C1 and the output 0 only determined by the C0. So you can write it as follows. So for C1, so what I want to do is basically I want to have the same bit, right, when O1 is 1, then the first 4 rows. Then I don't want to have the same bit, which is K, for the remaining rows when the O1 is 0. So this means that I will have M's here. So I'm not writing 1 or 0, but I'm writing K and M's. For the C0, and I want to make sure that these 3 rows are determined by a single bit, by a unique bit. And this means that let's use Y here for these 3. And for the rest, that I don't want to use the same thing. So this means that I will have Z's. So here what it says that K is not equal to M, and Y it does not equal to the Z, right? So, but what you can see here as well, so basically, if you give K, for example, 1, then this means that M will be 0, right? And in that case, so let me also put that up into, so for example, when you give Z1, 0, then this means that Y will be 1. Okay? So you can play with it as you want. But so when you use, for example, these bits here, then you'll have your representation for A, B, C, D. Right? So you can play with those. You can select K 0, and then the rest will be assured accordingly, basically. Did you get that idea, or? Okay. All right, then let's present A as, then this means that A is 1, 0, B means K1 and Y1. C means, so I have M here, 0, right, 0, 1. And D here, I have M, 0, 0. Okay? So let's write, then, okay, let's write it in that sense. Yeah. So I have A here, then C1, C0, and 1 and 0. This is 1, 0. This goes to B, then this means that this is 1, 1. I have, this goes to C, this means that 0, 1. 1, 1. This goes to C again, C is 0, 1. B is 1, 1 again, and it goes to A, which is 1, 0. I have C here, 0, 1, and this goes to D, which is 0, 0. And for D, goes to B, which is 1, 1, and again for D, that goes to D00, all right? So, yeah, that's a bit long, so if you allow me to save some time, I'm gonna directly write the Boolean equation, because what you do is basically I'm gonna again check the rows that are 1 here and the rows that are 1 for n0, and then I'm just gonna write as is. So this will be C1, C0 naught, and TB naught, C1, C0, TA, I guess, and C1 naught, C0 naught, and TB, and this will be simplified as C0 TB naught, or C1 C0 TA, and for n0 I will have C1 C0 not here, or C0 TA not, or C1 C0 not, and TB not. And for O1, I already ensured that this is determined by C1, and O0, this is determined by C0. Okay. So this is the F1. The last question asks, right? So the last question says that, so which one would you choose to minimize the total area of this FSM? So if you count the number of logics in the Boolean equation that I write, so you'll see that we have 10 logic units for one hot encoding, and I have 2 bits to represent the states. And for binary, I have 11 plus XOR. This would make 14 and 2 flip-flops. And for output encoding, I have again 10 logic units and 2 flip-flops. So in that manner, so using output encoding makes sense over the others. Okay. Is there any question? All right. I guess we can move to the next.
This question has 2 parts. In the first part, it's warm-up, computing a Fibonacci number. So this is about writing MIPS code to compute the Fibonacci number. And as you know, this is the expression for the calculating Fibonacci number. And here you have a high-level language code, C code, to calculate this Fibonacci number. So as you can see, we have 3 variables. We have A originally is equal 0, B is equal 1, and this is C, that is equal A plus B. And then we get into this while loop that will be repeated like n minus 1 times. And in the loop body, what we have is we first compute A plus B and store the result in C, and then we store B in A and C in B. So finally, we decrement this counter n, and we repeat the loop while n is greater than 1. So here there are some assumptions, conventions, to write our code. But let's say that the most important thing for now is that the argument n, that is this counter here, is going to be stored in register 4, and the result C, this C here, is going to be stored in register 2. Then there are also some register numbers, for example, for Kali save temporary registers. We're going to need these because, as you will see in the code, this Fibonacci computation is going to be in one function. Then we have the stack pointer. We're going to need the stack pointer, as you might remember, to save the temporary registers. And we also need one return address because, as you remember, every time that we call a subroutine, we call a function, we need to store the return address somewhere, and the return address is the return program counter, and this is typically stored in register 31. So let's take a look at this code. Yeah, let me do something so that you can see the code. So the very first thing that you find in this function, in this Fibonacci function, is that, well, this is the beginning of the function, and the very first thing is storing the registers into the stack, because some of these registers might have some values that are used for the main, are useful for the main function. But these registers might be needed by the function itself. You know that the number of registers in every computer, but especially in the MIPS computer that we have studied here in this course, it's quite limited, so it might be necessary to use some of these registers that are already being used by the main function, the caller function. So that's why the first thing that we have to do is saving the registers, in this case, registers 16, 17, and 18. 17 and 18. We store them in some part of the memory that is pointed by the stack pointer. And right after that, we initialize the registers with some values because we are going to use them. Okay? You had one question? Excuse me, you had one question?
Yeah, well, I just one simple question. Initially, but it's not relevant to what we're doing right now.
Oh, okay. Then you can ask maybe later in the break.
Yes.
Okay, so observe that, well, let's say that this is the function call. So this is the beginning of the function. Right after starting with the function, we have to store some temporary values in this stack. And right after that, the first thing that we do is this first C equal A plus B. So this is an addition. We store C in register 2. In register 6, 17, and 18, we have A and B. So this corresponds to this first C equal A plus B. And now, the next thing that we are going to find is this while loop, right? So in the while loop, the first thing we do is checking the boundary condition. So here, this is n must be greater than n than 1 to get into the loop body. And this is what we are doing with this set on less than immediate. We compare this register 16 that contains n. We compare it to 2, and if register 16 is less than 2, then register 3 will be equal 1, right? Observe that if it's equal 1, it won't branch, right? So it will go, if this is equal 1, it's not equal to 0. So if it's not equal to 0, won't take this branch, so it will go to the loop body. And what do we have in the loop body? Well, the first thing that we have is, again, add to 17, 18, that is C equal A plus B, corresponding to this instruction here. Then we store B in A. So that's why what here we are essentially doing is adding B plus 0 and storing it in A, in register 17. We do the same to store C in B, and after that we decrement -1. This is immediate addition -1 to decrement N. Right after that, we have this unconditional branch, this jump instruction, to start again and evaluate again the value of the content of register 16 that contains N. So we repeat this as many times as needed. When 16 is 16 contains N. When 16 is lower than 2, then this will be 0, and then here we will take the branch and we will until this down here, and we will finish the loop. And the very last part that you can find here in the code is this restore, because remember that in the beginning what we did was storing the content of these temporary registers in the stack. Now, right before leaving the function, we have to restore the contents of the registers. Yeah. Do you have any questions here? Go ahead.
In the labs, we were using those other names for the registers.
Yes.
A0, but that's 0.
Yeah.
Can we put it in the test, or do we have to know the exact?
So in the exam, what I recommend you to use is to do the notation that the question itself is using, right? So in this case, we are using the numbers. In other case, you will use the error something. But as you know, and actually you can check in the slides, they have the same meaning. Yeah. Yeah. Go ahead.
Are we saving the return address inside the stack just as a formality, or is it done because it's not overwritten?
Yeah, exactly. It's not overwritten. This is just a convention. So you can save it in case you might need to use this. But this is just a convention.
But it would not be wrong.
It would not be wrong if you don't overwrite it. Okay?
I thought my question before was about the name of the registers, but the way we're using is basically just a convention. Can use any for any purpose.
Well, I mean, usually if you have in the final exam some similar question like this, we will probably give you this kind of convention. If we don't give it to you, you are not required to know exactly this, but you can check in the slides and you will see what are the typical registers that are used for some particular purpose. Okay?
But there are these preserved as the code registers and the ones that are not preserved. So basically, it's just a convention we use to right?
It's just a convention, exactly. I mean, if one question like this asks you to stick with some convention, you should stick. It's not more than that.
I don't understand why you need to store the values of the register first in memory, because register 16 to 23 are colleagues. It doesn't mean that the call don't can store important values there. Or why do you have to store the values in the memory, the first part and the last part? Why do you need to do them on the list?
So they are Kali safe because they are saved by the Kali, right? This doesn't mean that the caller cannot use them. Before calling the function, before calling this Fibonacci function, we have some other function, maybe a main function that calls the Fibonacci function, and this main function might be using these registers. If we have this convention and every time that the function is called, we store these registers in the stack, we are on the safe side, right?
So it's just for safe.
Yes, exactly. It might, I mean, this, keep in mind also that you write this Fibonacci function just once, right? And then you might need to call it from different place in your main program or in different programs. And sometimes you might be using these registers, sometimes not, okay?
Yeah. So would it be possible, in this case, we don't need a variable, so we could just use the caller, say, registers, and then we don't need to, say the content of those registers on the stack because they're caller, say, so in the calling we can just use them as we please.
I mean, it's, your question is related to his question. In some particular situation, you might be able to do that, but the thing is that you are going to write this function just once. You just want to write this function once. And you know that in this function, there are 3 registers that are used, that are 16, 17, and 18, and you're going to operate using them. It might happen that sometimes you're really using these registers, other times not. But it is safe to have this convention that those registers that are going to be used by the function are by default safe in the stack. And this way you avoid any possible overwritten.
This just prevents a bug in case anyone does not support the convention of caller state and calling state function.
Say again?
Because we could just use as for a convention stated in the exercise and produce it just from A to B.
Yeah, sure. But how do you know that these have not been are not in use by?
We can't know for sure, but by the convention they should be caller state. Because we don't know for sure, we just do it.
Yeah. Okay. You had another question?
Yeah, during the semester we saw MIPS as well as LC3. We have to know them both really well, or is it more focused on MIPS?
Well, I think that you should know really well what Professor Mutlu has explained in the lectures and and ideally also what you have in the optional homework. Yeah, it's a reasonable answer.
We mainly see exercises which they always talk about MIPS. We see MIPS the whole time. So
there are also several lectures where we have talked about LC3B, and also there are a few exercises in the homework. Yeah, in this homework 3, for example, there are at least 3 or 4. Sure.
So what do you mean exactly about knowing about the instructions? If you're asking about semantics of the instructions, it's something that we should provide in the exam.
Okay, yeah, exactly.
So you should just know, you should just have general understanding of how assembly programming moves.
Okay, but
so we would need to know what parameters LST or LSTI, or in what order they take parameters.
No, so usually we clearly define. So if, for example, an instruction
Can you
defines
speak up? Can you speak up?
Yeah, sure.
Yeah. Actually, you can use this one.
Yeah, so basically, when we provide the instruction definition, we also provide the semantics. So we tell this register is the destination register, and those 2 are the source registers. And basically, the exam should know exactly what instruction is doing what.
Yeah, it's on if you want to switch it off. Okay. Shall we continue, or do you have any other questions? Okay, let's go to part 2. And here, MIPS assembly for rep mob SV. So here we are asked to write some code some MIPS code that is going to do essentially what one x86 instruction does. And this is x86 instruction is this rep mob SV. The mob SV part means that we are moving bytes, and the rep part means that this is going to be repeated several times. This instruction has 3 registers. There is one count register, this ECX, and then we have one source register and one destination register. This source and destination are 2 pointers to 2 different arrays, and what this operation does is for several times, and this number of times is the content of this register ECX, what we do is copying byte by byte from the source array to the destination array. And after each of these copies, these 2, ESI and EDI, are incremented. So part A in this question, sorry, what's wrong here? Okay. Part A in this question is asking about how to implement this in MIPS. So, yeah, this actually has some similarities with the first part. In summary, what we are going to have here is, if we, let's say, we write the high-level language code for this instruction, we would have something like this, right? ECX. Greater than 0, because ECX is the counter, right, where we have the total number of bytes that we need to copy, and this would be something like EDI ECX equal ESI ECX. This ECX would be like our counter and also index to these arrays ESI and EDI, and after every iteration we decrement. So this would be like the, let's say, the high-level language code to implement this rep mob. And here what we have is the MIPS code. There are we assume that ECX is stored in register 1, ESI is in register 2, and EDI is in register 3. The first thing that we do is checking what's the value of register 1, that is the value of our counter, and if it's not 0, we will go to the loop. And in this loop, as you can see, we load 1 byte, we store this byte in the corresponding memory position. These memory positions are determined by register 2, that is ESI, so the pointer to the source array, and this one, register 3, is the pointer to the destination array. So right after that, we increment register 2 and register 3 to point to the next byte, and we decrement register 1 that contains ECX, so it contains our counter. And after that, we check, we check what's the value of register 1, if it's still greater than 0. If it's greater than 0, we jump, we branch to the beginning of the loop body. If it's not, then we go to the rest of the code, to the following instructions. So it's very similar to what we did before, and I think it's quite easy to understand. So don't know if you have any questions. So let's continue and go to part B. In this second part of the exercise, it says, what is the size of the MIPS assembly code you wrote in A in bytes? How does it compare to rep mob SV? And it says, note, rep mob SV occupies 2 bytes, right? So this Intel x86 instruction occupies 2 bytes. And the question is, how many bytes occupies in memory this code that we have just written? Well, as you know, in MIPS, every instruction is stored in 4 bytes. And if you count the total number of instructions, this is 7. So the total size of this code is 28 bytes compared to the 2 bytes of the original instruction in the x86 ISA. Let me finish with this question and then we take our 15-minute break. Is that okay? We will finish very soon. Part C says, assume the contents of the x86 register file are as follows before the execution of this instruction. And these are our registers, the content of these registers. And it says, now consider the MIPS assembly code that we have just written here, how many total instructions will be executed by your code to accomplish the same function as the single rep mob SV in x86 accomplishes for the given register state. So the given register state is this one here, and as you can see, this register ECX has this value. This is hexadecimal representation, but if we convert it to decimal representation, is this number here. So, because this ECX register tells us the number of times that the loop, this loop here, is going to be repeated, the total number of bytes that we are copying, and the body of the loop has 6 instructions, the total number of instructions executed in this case is 6 times the value of register ECX, plus 1, because remember that in the beginning of the loop we had this BEQ instruction. So this is our total number of instructions executed for MIPS compared to one single instruction that will be executed if we have an x86 ISA. The last part, part D, is exactly the same. So the question is exactly the same, but the contents of the register file in this case are different. And if you observe the value of ECX in this time, it is 0. So if it's 0, we are not going to enter the loop. Right? If it's 0, this ECX is 0, this register 1 is 0, so we don't execute this loop body any single time. So the total number of instructions that are executed in this case with these contents of the register file is only 1. It's only the first BEQ instruction that you have in the code. Is that clear?
Consider 2 pipelines machines implementing MIPS ISA, machine 1 and machine 2, right? We have both machines have the 5 pipeline stages, very similar to the 5 basic pipeline stages that we saw in class, and one ALU. So the first machine is machine 1 does not implement interlocking, so it cannot detect dependencies on hardware. It assumes all instructions are independent and relies on the compiler to order the instructions such that there is sufficient distance between dependent instructions. So it's the compiler who has to deal with the dependencies. The compiler either moves other independent instructions between 2 dependent instructions, if it can find such instructions, or otherwise insert knobs. Assume internal register file forwarding. So an instruction arrives into a register in the first half of a cycle, and another instruction can correctly access the updated value of the same register in the next half of the cycle. So this is important, internal register file forwarding in this machine. And we assume that the processor predicts all branches as always taken. Okay, the machine 2 implements data forwarding in hardware. On detection of flow dependency, it can forward an operand from the memory stage or from the write-back stage to the execute stage. The load instruction can only forward from the write-back stage. So the load instruction only from the write back. Because data becomes available in the memory stage, but not in the execute stage like for other instructions. So assume internal register file forwarding, the same that in the previous machine. So the compiler does not reorder instructions in this case, and assume that the processor predicts all branches as always taken. Okay, we have this piece of code. You have this piece of code, load and store and add, immediate and a branch. And these are the initial values. So basically, we have dependencies here. These two instructions are dependent. We load in register 2 and we store register 2 into memory. And these two instructions are also dependent. So we add in this, we store the result of the add in this register 1, and we compare register 1 with register 25. So we have register 25 here, the content is 25, so we execute this loop basically 25 times. Because the initial value of register 1 is 0, so we increment each time, in each loop we increment this register. So when the video code is executed on machine 1, the compiler has to reorder instructions and insert knobs if needed, while the resulting code that has minimal modification from the original. So for doing that, I'm going to draw the pipeline stages. I think that it's easier to solve in this way. So if we have this load, so we have the fetch, decode, execute, memory, and write back, right? So to execute the store, we need to have this register content. And we see here that we assume internal register file forwarding. So we can, so in the same cycle that we write back in the load, we can read from the store. So at this point, in the write back, we can read from the store. And we read registers in the decode stage. So we can do this. So this is the store instruction. This is the load instruction. This is the store instruction. So the best we can do is have the store here. So this is decode. This should be fetch. Execute, and write back. So we have some bubbles here. We have two bubbles here. So let's see if we can fill this, right? We can fetch here, and we can fetch here two more instructions, right? So let's see if we can reorder the next instruction. So we see that these two instructions are independent of the previous one. So we can insert this addition before. So we can put this addy here, right? So we can put this addy here. And then we cannot put, so the branch is dependent on the addy, the same. So to read the content of register 1, you have to wait for this write back, right? So we will need to execute the decode in the write back. Let me check. Yeah. Okay. So so basically here we have to insert an op. So this will be execute, decode, execute. Yeah. Oh, I'm sorry. Execute, modified, write back. And the last instruction, branch, can fetch. So this is not very well aligned, but this is the decode phase, so we can So when we grab that here, we can read the register from here. So we can execute memory write and write back. So this is basically the code that the final code that we need to, that the compiler needs to generate to execute this code correctly in machine 1. Any questions here? Okay. So next question.
What's not specified here, it's not specified that it is or that it is not, is the branch resolution latency. Are branches evaluated in the decode or not? It doesn't specify here.
So
Because usually when something is not the case, it specifically says it does not have any kind of warning, basically. But here it's basically left out. So can I make an assumption?
yeah, of course, you can make an assumption. In this case, I'm assuming that yeah, you can resolve the branch. So here, the processor predicts all branches are always taken, right? This is a very easy branch predictor, so you can always assume that it's always taken, so you don't have any extra latency here. You can, yeah. More questions? So next question is, when the given code is, so I will answer, you cannot see this, right? Okay. So I will let this question to the end, and I will go to the question C, because I think that is easier in this way. So calculate the machine code size for the machine code size of the code segments executed on machine 1 and machine 2. So in machine 1, we have basically 5 instructions. So we have 5 instructions, and each instruction is 32 bits, so, or 4 bytes. So we have 20 bytes. And in machine 2, we have exactly the same code, so the compiler doesn't insert anything. So we solve the dependencies of hardware. So we have 4 instructions. So we have 4 by 4 bytes. That is 16 bytes. So point D. So question? Yeah.
Yeah, isn't that a loop? So don't we have to multiply? Would the compiler write?
No. This loop is executed dynamically, right? But you only need 4 instructions.
Okay, so
for the static instructions.
Okay, the machine code would split it up in a linear, just going through it, but it would also.
Yeah, you iterate. You make a loop over these 4 instructions, right? Yeah. In that case, if you have a loop of an infinite loop, you will have infinite source code. It doesn't make sense, right? Yeah. So calculate the number of cycles it takes to execute the code segment on machine 1 and machine 2. So for machine 1, you already have this diagram here, right? This is cycle 1, cycle 2, cycle 3, 4, 5, 6, 7, 8, 9. So this is one iteration of the loop. So in one iteration of the loop, you see that you can issue 5 instructions. So, and the next loop can start immediately after these 5 instructions. So, as we have 25 loops, and we can start 5 instructions per loop, so we have 125 cycles. But in the last iteration, we have to finish. So imagine this is the last instruction. So we have to execute these final pipeline stages that are 4 additional cycles, plus 4 cycles. This, yeah, 129. Yeah.
Wouldn't it be 25 times 4? Oh, no, okay, we have the
Yeah, this is... so calculate the number of cycles for machine 2. So let's go to machine 2. So in machine 2, we have, I will do it. Yes.
The question I had before was about this exercise with the 129. This is computed by, you have 125 cycles, which are cycle repeated.
So these are actually these are instructions, right? This is the number of instructions.
Again, there's a branch. So do we have to count? It starts loading the instructions that come after, even though it is.
I don't think so. So it's only the number of cycles of this loop, right?
No, yeah, but it says the branch predictor guess is always taken. So in this case, you would start loading the next one before you notice that you have to stop executing it already. Or you just
Yeah, you just will, in that case you just will you mispredict, right? But your loop will be executed already. So
also we don't. Oh yeah, that's so don't care.
you don't care after that. Yeah. So for machine 2, okay. For machine 2, we have this code. So we have first the load, that is fetch, the code, execute, memory, write back. Then we have the store. So on the store, we've seen the definition of the machine 2 that the load instruction can only be forwarded from the write back stage because the data becomes available in the memory stage. So the data becomes available here. So from here, we can forward this data to the execution stage. So it's specified here, right? The forward from the memory or write back stage to the execute stage. So this data can be forwarded from the write back stage to the execution stage directly, right? So we have this here. Yeah, we have the code. So we have to store here. We are not ready to execute in this cycle because we need to wait for the data here. So next instruction is addition. Basically, we fetch the addition. We have to wait because the decode stage is occupied. And then decode. Well, here I missed the other stages. Decode, execute, memory, write back. And then the last instruction is the branch. So the branch can only be fetched in this stage because this is occupied by the previous instruction. So here we have a dependency. In these dependencies, so we can forward from the memory stage in this case, because this is not a load instruction. So here we can forward data from here to the execution stage, right? So we don't need to wait in this case. So the question is asking for the number of cycles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles. So we have in each loop we need 5 cycles, and then in the final loop we need 4 additional cycles to finish the last instruction. So basically, it's the same number of cycles than the machine 1 and machine 2 executing the same number of cycles, 129. Yes.
Something that is not really clear, that's also been an issue in another homework, is that to me the forwarding, the effectiveness of the forwarding is dependent on the dependency checking method. If you use scoreboarding, from memory to, if you use scoreboarding, right, then you do bypassing from the memory stage to the execute stage. It wouldn't work for me because I wouldn't have left decode stage because the valid bits aren't 1 yet. So there won't even be a situation where I get the data forwarded from memory to execute because I wouldn't be in execute stage yet because the valid bits aren't set yet. You see my problem? It works in the book. It has a hash detection unit or what it's called. Then it works, but with scoreboarding, it for me doesn't.
So here it doesn't mention anything about the how this is implemented, right? So you have to take the information that you have in this in the question. So what the question says is exactly what we did here, right? So how it is implemented in hardware is another question. But
to me that would be relevant. I mean, I would just make an assumption, right? I'm assuming that it would be done in this way. Because for me, if you have dependency checking based on scoreboarding, write back to execute forwarding doesn't make sense. I mean, I'll probably ask it after or in the break.
Okay, but okay, we can discuss later. But yeah, basically, but here the exercise is pretty clear in that sense, right? Yeah, it doesn't talk about how this is implemented in the hardware, but so you assume internal register file forwarding, so an instruction writes into a register in the first half, and other instructions can read in the second half. This is for register forwarding, and for the other forwarding, it can forward an operand from the memory stage or from the write back stage to execute the stage. So the load instruction can only be forwarded from the write back because the memory, the value is ready in the memory stage. So in the next stage, you can forward to the execution stage. Yeah. So the underneath details are not specified, but we have to assume that we can do this, what is specified in the question, basically. So, and the last question is, so I let this to the end because once we solve all these questions, it's very easy to solve. So when the given code sentence is on machine 2, dependencies between instructions are resolved in hardware. Explain when data is forwarded and which instructions are stalled and when they are stalled. So we already see that we stall here, and we have data forwarding in here and here. Okay. Questions?
Okay, so we will continue with this question on Tomasulo, and I think Professor Mutlu already showed some example during the lectures, but I think this is an important concept that we can go over once more. Okay. So I'll just quickly read the question. So this is kind of a question that doesn't require too much computation or too much knowledge exactly about how the algorithm is working, but it's asking more about the overhead and like how many functional units or comparators you need in your design. So it basically defines those properties where you have 8 functional units and 32 registers, and each register is 64 bits wide. And then you have 16 reservation stations entries per functional unit. And so basically you have a reservation station for each functional unit, and you have 8 of those, right? And each reservation station will have 16 entries. So this will basically look something like, let me see, oh, this is so ugly. Yeah, so basically it will look like this, right? So you have some functional units here. Okay, I can't draw very well, but you have 8 functional units in total, and each functional unit will have its own reservation station. Okay, and we have 16 entries in total per reservation station. And there are as many reservation stations as functional units, right? Okay, so this is so far what the question told us. And also there are 32 registers, 32 architectural registers. And then again, importantly, each entry in the reservation station can hold up to 2 source registers. So basically, this is like, so this is exactly the same reservation station that we saw, that we had in the slides during the lecture. Basically, here we have 2 source operands, right? And then it has separate tag fields for each source field. I guess you can see it. And then separate data fields. Yes, so it looks something like this. And the question is asking about how many tag comparators are there per reservation station entry. So if you go back here, so in a single reservation station entry, we have two tags, right? Because we have 2 source operands. And so we will need a comparator for each tag for each functional unit, right? Because at this, in the same cycle, each of those 8 functional units can produce a result, and this result needs to be compared with each of the tags in the reservation station entry, right? So we have 2 tags here, and we have 8 functional units. So basically, it means that we will need 8 multiplied by 2 times tag comparators. Okay, is it clear? Yeah. So basically, the result coming out from this function unit will be compared against this tag and this tag. So same for this functional unit, right? So it will need to be compared against those 2 tags. And the same is true for all functional units. Basically, we will need 2 comparators per each functional unit. Then the answer is 8 by 2, which is 16 tag comparators per reservation station entry. Okay, is it clear? And then the second question, B, is what's the total number of tag comparators in the entire machine? So this is kind of like tricky, because if you just think about reservation station entries, you may not take into account the RAT, register alias table, right? Because it should also have some comparators, because when you calculate the result, you don't need to only update the reservation station entries, but also the register alias table, which is not shown here. But if I draw this, the register alias table will be basically, it will have 32 entries, because we have 32 architectural registers, right? And then it will have data field for each entry. It will have some tag field, right? And it will also have some valid bits. Okay, so basically, we also have some comparators here, right? So one comparator for each tag. And then it will be again multiplied by the number of functional units, because in a single cycle, we will need to compare those tags against each of the results coming out from the functional units. Okay, so if we accumulate everything together, so we have 16 tag comparators for each entry, right? And we have 16 entries in a single reservation station. And then we have 8 reservation stations in total. Okay, so those are the total number of tag comparators for the reservation stations. For the register LD table, we will also need 32 multiplied by 8 comparisons. So here 8 again is the number of functional units we have. Yeah, and you can calculate this. Okay. What is the minimum possible size of the tag? So this depends on how many entries you have in your all reservation stations, right? So as we show here, so you may have in a single reservation station, you may have 16 entries for which you can do some computation and produce a result, right? So so you can remember this from the slides that we address those as A, B, C, and etc. Right? So basically, those are the addresses of those entries, and you need addresses as many as the total number of entries you have in your system. So there are 16 entries in a single reservation station, and we have 8 reservation stations in total, right? Which makes 128. So this is the number of address. This is the address space that we should be able to address, right? And basically, this is equal to 2 to the 7th, and this means we need 7 bits as a tag to be able to address or refer to all reservation station entries. So the minimum is 7. Of course, you can have more than 7, but then you'll have some redundancy, right? Some useless bits. I guess nobody has any questions. Okay. And then what is the size of the register alias table in bits? So the register alias table is, it should look something similar to this thing here that I draw, right? So we know the tag that should be at least 7 bits. And then the data is given in the question. So the architectural registers are 64 bits wide. So then per entry, we will need 64 bits. And then we should have at least some valid bits, right? So for a single entry, we will have 72 bits. And we have 32 entries in total. So it will be 72 multiplied by 32. And I guess, so just let me check if I'm missing anything. Yeah, I think, yeah, that's it. So this is the total storage needed for the register alias table. And then the last part is, what's the total size of the tag storage in the entire machine in bits? So it only asks about tag storage right now. So we should include the tag storage in the register alias table as well as in the reservation stations. So in the reservation stations, we have 2 tags per entry, right? So it is 14 bits because we know the tag is 7 bits. So it is then 14 multiplied by 16 because we have 16 entries per reservation station and there are 8 of them, right? So this is the tag storage for the reservation stations plus the tag storage for register alias table, which is 32 multiplied by 7, right? We have only 7 bits in each entry. Okay. guess, is this correct? Is the total minimum size with text storage and entire machine in bits? Okay, yeah. Okay. Everything clear? I think that this was a relatively simple. Okay, the next question is on out-of-order execution. We solved a very similar question during the first discussion session, if you remember. So this is basically testing your knowledge in Tomasulo's algorithm. And I will just highlight a few important things here in the question. So there's a one-cycle fetch and one-cycle decode stage. And this machine can execute two different instructions, add and multiplication. And each of those take different numbers of cycles in the execution unit that they are executed. So those execution units, the adder and the multiplier, are not pipelined, and the addition takes 2 cycles and the multiplication takes 3 cycles. Let me see quickly if there was anything else that was important. I guess not for now, but I will refer to the text here in the question later. So let me move to the questions, but before that, so these are the state of the register LE table, RET, and reservation stations at point where all the instructions are fetched. And this program has 4 instructions, which is also highlighted here. Okay, so this is the state of those structures after dispatching all of those 4 instructions. And dispatch happens during the decode stage. It's also written here in the question. So the first part is to find out what are those instructions, including the destination register, the type of instruction, and the source operands here, the source registers. So I will fill this table here on this side so we can see everything in one place. Okay, so the first part is very simple, like figuring out what are the instructions. You basically look at those tags over here in the reservation stations, and usually there's a dependency which helps you figure out which instruction comes first and which comes after. So from the question, we know that the instructions are issued to the instructions are allocated to reservation station orders, reservation stations in top to bottom order. Okay, so here when we look at a single reservation station, we know that this instruction comes before this instruction in the program order. Okay, so we have to start by looking at the first entries here in the 2 reservation stations. So we can easily tell that this instruction over here, the multiplication, comes first before this instruction over here, because this is dependent on the multiplication, right? So the D tag is here as a source operand to this addition instruction. Okay, so the first instruction is multiply. What is the destination register? So for that, we have to look at the register LE table, right? We don't see any D, which means it is overwritten by one of the next instructions. So we have an instruction that comes after this multiplication that writes to the same destination register. So let's call this destination register X for now, since we don't know what that is. And the source registers are R1 and R1, which we can tell based on this information here, right? So the source operand is valid and it is 5. And only R1 has its value set to 5. So the 2 source operands are R1 and R1. So next instruction would either be this one over here, identified by tag E, or the instruction that has tag A. So here, deciding which one comes first is again very easy because we have a dependency to A here. So A should come first, right? And the second instruction is add. It writes to R1 register. And its source operands are, one of them is, so it's dependent on this instruction. So this source register should be the same as the destination register of this instruction, right? So it should be X. And then the next source register is 8. The value of the register is 8, which corresponds to R2. Okay, and then the third instruction is either B or E. And since E is dependent on B, we can tell that the third instruction should be B, which is an addition, which writes to destination register 4, R4, and the source operands are A and A. A was writing to R1, so the source registers are R1 and R1. And the last instruction is multiply, writes to R3, and source registers are R1, and B was writing to R4. Okay. Yeah, so this is the program basically, and we couldn't find any clue like what is X here, right? So it could be R1, since R1 is overwritten by this instruction over here, or it could be R4, or it could be R3. So it could be any of those instructions, and nothing changed based on like which register you put here. So like let's say is R1, like when we do the next parts of the question, but you can assume this to be any of those 3 registers basically. Or maybe you can just leave it as X. But basically, in the solution, you have to make it clear that you understand that this could be any of those 3 registers, okay? So just like, don't just leave it blank. Put something like X and explain that it could be like one of those 3 or 4 registers. It could be one of the 3, yeah. Okay, so this is the program. And yeah, we are done with part A now. And part B is basically simulating that program on the processor that was given, and we have to fill this chart over here. So let me quickly write these instructions here. So it will be easy. This was R1. This is R1, R1, R2. Yeah, I should have written those here. R4, R1, R1, R2, R1, R4. Okay, and then we have to fill the rest of the table. So we know that this processor has a fetch stage of 1 cycle. It has decode. Multiplication instructions are executing in 3 cycles. So we will have 3 execute stages in here. And then, and we have write back. Okay, so this is the first instruction. The second instruction, we can fetch here. We can decode and dispatch here. But since it has dependency, it has to wait until the end of the write stage to execute. So it will start executing here and we'll do write back. So in the question, always like this information will always be provided. So try to find this part to determine whether execution can start at the same cycle in which the destination register is written, or it can start after it. So in this specific question, it cannot start, so I cannot put E here. I have to put E over here after the write back stage. And that information is, let me find it. Yeah, a dependent instruction can begin execution in the next cycle after the write back, if it has all of its operands available, okay? So it's simple, and then for the next add, it is the same, so we can fetch and decode it here, but we have to wait for R1. So again, we have a dependency, so we can execute it here and write back. And then the last instruction, again, we fetch and decode it, and to execute it, we have dependency to R4, which is this instruction. We can execute it over here and write back. And I feel like I made a mistake. I think it was supposed to take 16 cycles. Can you see where I made the mistake? Anybody? No? Okay, maybe it was 15. Maybe I remember it wrong. Oh yeah, okay. Okay. It should be 3 executions and write back. Okay, that's it. And we are done with this part too. Let's take a look at the last part, unless you have any questions. Yep.
I don't see how the third instruction could get into decode. No, wait. It leaves decode stage and goes to reservation station. So decode stage is free again, right?
Yes.
Okay, then I understand.
Yeah. So this is slightly different from in-order execution, where usually we do the register fetch, fetching the source operands at the decode stage. So here, that's not happening at decode, right? So you are not accessing necessarily the register file at decode. You are just like allocating a reservation station entry and filling it accordingly with all the dependencies. Okay. And the last part is updating those 2 structures based on how they would look at the end of the 12th cycle, basically here. So what happens at the end of cycle 12? This instruction completes, this instruction completes, and this instruction also completes. So in the reservation station entries, we should only have this 4th instruction, right? Other entries should have been cleared. Let me see if I can put this side by side. Almost. Okay. I hope you can see it. Okay, at least you can see the first part. Okay, so we know that this was the first instruction, this is the second, this is the third, and this is the last instruction. So this is finished, so I'll just put dashes here at the end of cycle 12. B is also complete. D is complete, so we don't have to fill anything here. And for E, since A is complete, it will have its data available. Here the value will be set. B is also complete, so this will also be set. So let's find out what are these values. So the result of this operation is 5 by 5, 25, right? And so D is 25 plus 8 is 33. So whenever we see 33, we can put, whenever we see A, we can put 33. And then, okay, so basically here we will have 33, and B will be 66. Okay, so I just executed those instructions quickly. So this is 33, and this is 66. And the rest is also blank. Okay, and to fill the register alias table, it is again the same thing. We already calculated the values, so we know A was 25, so this will be updated to 25. R2 is untouched. R3 is set by this instruction. It's not complete yet. So, sorry, this is E, this is 0, and we don't have the value. And then R4 is B, which is 66. Okay, that's it, basically. And this was the last part. Okay, just like when solving this question, just be careful to read that part carefully, or like you don't have to read it at once, but be careful when you need like to like make sure like what kind of information is provided. For example, when you realize this part, like whether you can put E here or you have to delay it 1 cycle, you have to like go back to the question here and look at what's provided. Okay. Any other questions? Then we will continue with the next one. Oh, there's a question.
Shouldn't it be 33 in R1?
Sorry?
Shouldn't it be 33 in R1 since we write A and not B?
Yes, you are right. Okay, yeah. This is A. I updated it by D. Yeah.
Just a general question about how you design the
Okay.
I don't know if we can solve so much faster than we did today. So do you expect this to solve 10 to 60% and just pick out the ones that we feel most comfortable with, or do you want to race through the exam?
So, like, I can answer this question like based on last year's like exam. There were students that like were able to solve all the questions. So when we design questions, we try to make them solvable in like approximately half of the time we are providing to you. So yeah, so we can usually solve those questions in 1 hour if we are providing you 3 hours. Okay, and here why we are still at 60% of the questions is because we are also explaining them to you. So if I was solving this question by myself, I wouldn't have been talking, right? And then spending time of like basically putting things in a way that you can see and understand better. So those things also add up. And also answering your questions take time. Okay, yeah.
Also another question regarding the exercises that we had. It's great that we had them, but it's just one example. Are there any other examples where I can try myself in out of order and fill up that RAT, stuff like that? Are there any exercises available from the last years that are different to this year's or not?
Yeah, I think you can check the links that we have in the website for the past courses, and then from those past courses you can check links for like even older courses, and then you will find like bunch of exam questions, bunch of homework questions, and you can also take a look at the architecture course, not only the digital design one. So some questions are similar basically. We'll continue with the next question, which is on out-of-order execution. So hopefully you remember the concept, so I will go quickly over this. So here's some definition of what kind of instructions we are dealing with in this question. So we have two types of questions. One is add, which has this number of cycles here and those stages defined. And Okay, yeah, as I said, so the add instruction has those stages here. I think in total it's 9 cycles. Yes, it says it here. And then for multiply instructions, we have 11 cycles in total. So 2 more cycles in the execution stage. And the question is also describing it well, like what is the policy for reading back the data. So it is basically when you have data dependence between 2 instructions, the instructions that that depends on the result on the previous instruction has to wait for the data to be written in the write back stage, and in the next cycle it can start executing. So the question has multiple parts. One of them is figuring out an instruction sequence that's composed of 5 instructions based on the information given in this table. So this part is how the values in the register file looks like before the execution of 5 instructions. And this is what happens after executing those 5 instructions. Yes?
In the previous question, we said that if there is a data dependency, we can only start a decode after the write back finish, and now we're assuming that we can start executing after the write back finishes.
Right. So that's because of the difference between in-order execution and out-of-order execution, specifically with the Tomasulo's algorithm. So here it is different a little bit. So you will see as we solve the question. But basically here, the decoding operation consists of allocating an entry and filling the entry in the not register alias table. So you also update the register alias table, but you also update the reservation stations, right? So I can show you how it looks here. So probably this will remind you from the slides you saw in the class. Okay, so basically the decode operation here is allocating that entry, but when we talk about in-order processors, then decoding mostly means reading the values from the register file. And obviously you cannot read the values before writing the new values into there, right? Okay. So here, how you can figure out what the instructions are just by looking at those two tables here, like before and after version of the same table, actually. So there's a hint in this question, which is the fourth instruction is given to us partially. We only don't know the destination register, but we know that it is the multiplication of R6 and R6, right? And when we look at before and after version of the register file, we can see that R6 is not modified, right? It remains as 10. So we know that the result of this multiplication will be 100, right? But we don't see 100 anywhere in the register file, right? So some other instruction has overwritten this 100, right? And there is only one possibility because we have only one instruction coming after this multiplication instruction here. So we don't know exactly what is the destination register, but just by considering this information, we can tell that the destination registers of those two instructions are the same. Okay, so let's start one by one. So if you look at those given values and the final values we get, so basically your approach here should be trying to reconstruct the final values using the values that we have initially. So for example, we can see that R7 is updated, right? So it is 21 here, it was 11 here. So we can basically look for values here in this like initial version of the register file to calculate this value of 21. So here the only option for doing that is adding together 10 and 11, right? So we cannot multiply 11 and 1 because we don't have 1 in the register file. So one instruction then should be an add which writes to R7 and uses R6 and R7 as source registers, okay? So this is basically creating 21 in here. So let's look at some other values that has changed. So here we see 31 in register 3, and the original value was 7, right? So now, given that we have 21 here in R7, we can calculate 31 by doing an addition, another add instruction, right? So we will be updating R3, and we will update it by, so it will be again R6 and R7. Okay? So we did that too. Other values that are updated is R0 and R2. So for R0, what we can do is, so we already calculated 31 here, and we have 10, and we have the multiplication instruction. So we can multiply those two registers and write the result to R0. So it will be a bit ugly, but this is the next instruction here. Actually, so initially when I was like solving this question, I was just writing down those instructions, but I decided to figure out their order later based on some other information. Okay, so here what I'm doing is only just writing down instructions that I can figure out by looking at this table. But it happens that all those instructions have dependency between them, so it's very easy to figure out the order. Okay, but if it's a bit more complicated, which I doubt that it will be in the exam questions, then you will need to look at some other information that will be given to you in the question, like the entire 5 instruction sequence completes in X cycles. Okay, so then you may end up with different orderings between those instructions, and different orders will result in different execution times, right? And then you can find the correct ordering by looking at the number of cycles. But anyway, so if we continue here, we said that we can get 310 to R0 by multiplying R3 and sorry, this is multiply R3 and R6. Okay, and then we know that we have something here, so this will be the fourth instruction. And finally, we will need to calculate, so we also updated this, we will need instruction to calculate 410. And it is basically the addition of 310 plus 100, right? So this is already giving us 100. And we know that we need to write the result here to R2. So this instruction here should be modifying R2, right? So let's write it here again, and then I will fill this. So it will be updating R2, and it will do so with adding to R0, it will add 100. So this instruction here will give us 100, right? And in the beginning, we said that it should be the same as this instruction that is following it. So that instruction, the last instruction, should also be R0 plus R2, right? So if you fill this here to have everything in written in a nice way, so this was the first instruction, this is second, this is third, this is fourth, and this is the last instruction, okay? So this is add to R7, R6, R7, then another add to R3, and again R6 and R7. And the last is here multiplication, R0, R3, and R6. Okay, is it clear? Did I miss anything? Okay, so that was easy. So in the next part, actually I also B and C together because they are sort of related. So basically in parts B and C, we have to execute Tomasulo's algorithm with this instruction sequence that we find in part A. Okay, so basically it will be filling the register alias table, which is this here, the register file, and also the reservation stations. So let me do it like this. Okay, you can see it. It's better. Okay, you can see almost everything. Okay, so one thing I forgot to say, it is asking specifically about the state at the end of cycle 8. So actually first it will be better to figure out what has happened inside the processor until cycle 8 or at the end of cycle 8. So here in the beginning, we were given with these stages that the addition and the multiplication is going through. So I will just write it here. So in the first cycle, for the add instruction, we will do fetch and then decode, and then we will go through E1, E2, E3, E4, E5, E6, and then it will be right back, right? So this is the first cycle, second, 3, 4, 5, 6, 7, and 8. Okay, so cycle 8 is where we are in the last stage of execution for the first instruction. Okay, so then at the end of cycle 8, we have no updates in the register table, right? In terms of final values here, because we didn't perform any write back yet for any of the instructions. But what happens is, until then, if I write it quickly, we have enough time until cycle 8 to fetch and decode all the instructions here. So we can fetch and decode the second instruction, we can fetch and decode the third, the fourth, and the last instruction, right? And we are still at cycle 7 here, so this was 6, right? 7 and 8. So somewhere here at the end of cycle 6, we have all the instructions decoded, right? So we fill them to the reservation stations. So I'll sort of do it quickly, but if you basically follow the scheme here, you can fill the reservation stations and register L is table one by one. So for the add instruction, so we know that at the end of cycle 8, we will just have the information recorded in the register L is table and the reservation station and nothing else, right? So let's fill this part first. So here we had the valid, tag, and value fields, right? Do you remember what those means? So tag is basically when you don't have the result calculated, but the result will come from another reservation station entry. And the tag is basically the ID of that reservation station entry, ABC for the addition unit and XYZ for the multiplication unit. Okay, so for the first instruction, we have the up-to-date versions of R6 and R7 in the register in the register file, right? So for those two source operands, the valid bit is 1. We don't have any tag because we are not waiting for the result to come from another reservation station entry, and we have the values. We can just look up from the register file, 10 and 11. So 10 for R6, 11 for R7. Okay, and then the next instruction is add to R3. So it uses R6 and R7, but R7 is updated in the previous instruction, right? So this time we cannot read R7 from the register file. So although the first source operand here will be again 1 dash and 10, so no tag, and it is valid. For the second operand, we will have 0 as a valid bit, and then we will expect the result from A, reservation station entry A, and we don't have the value. Okay, so when this instruction in A completes, it will update this field over here. Okay, and the next instruction is multiply. So for multiply, we don't have R3. We are expecting it from here. We don't have R6. Sorry, we have R6 in the register file. So it will be 0, and we will get R3 from B. We don't have the value. And for R6, we have the value, which is 10. Okay? Is it clear so far? So you basically continue in the same way. For the second multiply, we have the R6 value in the register file, so we will just have the valid bit set and the value here. And for the last instruction, we will get the first source operand from here, which we put into reservation station entry X, and R2 will come from reservation station entry Y. Okay, so this will be X, this will be Y. Both are not valid yet, and then we don't have the value. Okay, so we kind of did it decoupled, but at the same time, when you are filling those reservation station entries, you can also update the register L is table, but it was difficult for me to fit both pieces of paper at the same place. If I do it, can you? Nice, okay. So this is easier to fill. So basically for R7, we are updating R7 here, right? We will have valid set to 0, and the result will come from A, right? Because this is where we put the, this is the reservation station entry we allocated for the first instruction, and we don't have the value. Or you can preserve the existing value, right? So we can just write here 11. But it is really a don't care value because we know that it is not valid because of the 0 here. Okay, so it is both fine to write nothing here or just to keep 11, the previous value. Okay, and then the next register we update is R3. So for R3, again, we will have 0 because none of the operations are committed until end of cycle 8. And it is allocated to B. Okay. And then R0 is again not valid, and then it's allocated to reservation station entry X, R2 is allocated to Y, and R2 is again allocated to C. So here you basically update this again, okay? So we don't have Y in the register alias table, but we have Y in the reservation station entry over here, right? So when this instruction over here, Y completes, it will not update the register file, okay? Because the most up-to-date version is supposed to come from C, from the next instruction, but it will update the corresponding reservation station entry over here, okay? So if you do everything sequentially, you will see that every instruction is getting the correct value, and at the end you have the final values in the register file. Okay, and the rest of this register alias table is basically the same as the before here. Yeah.
Would in this case then make sense to fill the register alias table from the bottom up based on the reservation stations? Because then we could never run into an issue where we write something in the register alias table and suddenly figure out, oh, there's a new rule value. Would it make sense to write it from the bottom up?
Yeah, you can do that, but so how Professor Mutlu was like doing this in his slides was also whenever you first allocate a reservation station entry, you also update the register alias table. So it is totally fine to do what I did here, to initially put a tag there, and then when the next instruction comes and overwrites that destination register, you update it as well. So it is actually what happens inside the processor, right? Because you do one operation at each cycle. Okay, cool.
So the question is about the Boolean logic and also truth tables, as it also writes here. So in this question, we have 4 inputs and also 2 functions which are directly related to these 4 inputs, and we are basically asked to fill this table and also write the Boolean formula for X and Y here. So these are our inputs, A3 to A0, and these are our functions that we're going to fill the truth table here. So let's look at the first, you can see it, right? Okay. So let's look at the first question here. The first question, it says, describes X first, and what X is basically, X is 1 when the input, basically all of the inputs, does not contain 3 consecutive ones in words A3 to A0. Or otherwise, in other words, it is 0 when it contains 3 consecutive ones, basically. So let's find such occurrences in this truth table. So for example, it contains 3 ones consecutively, right? So then this means that here X should be 0. And we also have 3 consecutive ones here. So here also X should be 0, all right? And the last one should be, the last one is here. So this is 0. But for the rest of these, X will be 1. Y basically, for the rest of them, I won't have any 3 consecutive ones. And let's just very quickly write this. All right. Okay, so, and the question says, we fill the table and fill the truth table and use product of sums. This is product of sums form to write the corresponding Boolean equation for X. So basically, let me write it. So what a product of sums is we have, so we have terms, and those terms are, sorry. So for X, we have such terms, and those terms will be ANDed to each other. This is basically the product of sums, and here I will have the ORs here. So what products of sums says us basically, this X will be 1 if all of these terms are 1, right? Or in other words, this X will be 0 if one of these terms is 0, basically. So I'm going to pick the second option here because it will be easier for me to write the Boolean equation. Why? Because I have fewer zeros, and I'm going to write my equation accordingly based on that. So basically, I'm going to try to make x 0 if one of those terms becomes 0, basically. I'm sorry? All right, so I didn't write anything yet. So let's first think the case when A3, A2, A1, and A0 is 1, 1, 1, and I will have 0 for x, right? So in order to have this, I need to have a term such as A3 not, A2 not, A1 not, and A0 not, right? And if all, and I have ORs here as well. So if I have ones for all of these, then this will be 0. Another term will be for this. So what it is basically A3, A2, A1, and A0 is 1, 1, 1, 0. So how can I write it in a term? Is basically A3 not, A2 not, again, or A1 not, and A0. So if you put 1, 1, 1, 0 here, then this will become 0. And the last one is basically that one. So I'm going to directly write it. Hopefully you understood the logic here. So it will be A3, A2 not, A1 not, and A0 not. Okay? And those are ANDed, and this is x, and this x will be 0 if one of these terms are 0, basically. So this is the solution for A. For B, it asks for the sum of products, and Y is basically is 1 when no two adjacent bits in the word are the same. Basically, what it means is that basically I won't have any adjacent input bits equal to each other, right? So this means that here, where is that? Yeah. Here, I don't have any adjacent input equal to each other, so this should be 1. And I guess here, yeah. Here, I also don't have any adjacent input equal to each other, then this should be 1, and then the rest should be 0, because for the rest of the cases, I will have at least two adjacent inputs equal to each other, so the rest is 0. And so what is sum of products is basically I have terms, those terms are ANDed, inside ANDed, and outside those are ORed. Right? So again, like in other words, so Y is 1 if one of these 1, basically. So let's then write it in that way. So to make Y 1, I have two options, either that or that, right? So this means that Y is or A3, A2 not, A1, and A0 not. So this is similar to each other, but instead I ORed the terms here. And I said that if one of these is 1, then Y should be 1. This is what the question is asking for, basically. So I think there's no question raised to that. So for C, all right. So for C, it says, please represent the circuit of Y using only 2 input XORs and AND gates. So this will be, I'll write the circuit in a very intuitive way, and also I'll show you the equation later, but very intuitively how you should be thinking is basically for Y, so I shouldn't have any 2 adjacent inputs equal to each other, right? So this means that those are basically XORs, right? So those shouldn't be equal to each other. So then how can I write it in that manner is basically So this ensures that those two inputs won't be equal, or it will give 1 when those are not equal to each other, let's say. For this one, this says that A2 and A1, when A2 and A1 is not equal to each other, then the XOR will give us the 1 again. So this is XOR. And for A0, probably you see where I am going. And here, similarly, this XOR gives 1 when these are not equal to each other. So basically, I'm going to AND those, right? And this is our very intuitive circuit. So if you need to prove that this is actually correct, I have something written here. So what you need to do is, let me see if you can see it, yeah. Yeah, what you need to do is basically, you need to write y in a Boolean equation and also take the De Morgan, right? And so when you take the De Morgan, you will have something like this. So you can distribute those in such a way that all of these will be cleared, and the rest will give you some bunch of XNORs and XORs, and some of the XORs or XNORs will be implicitly included in other XORs, and then you will also end up with the same circuit. All right, if you don't have any questions related to that, we can take a break. Yeah. I'm sorry? No, the question asks for you the circuit, right? So if you show the circuit, but like be careful, like make sure that you do what the question is asking for. For example, if the question says that use the Boolean algebra and not, for example, K-map, don't use K-map, but use Boolean, such as like those are the details. But if the question is asking for the circuit, it's enough for you to show the circuit, yeah.
It's about data flow. Do you remember data flow? So it was kind of early in the lecture. I think it was on the, I don't know exactly which week, but it has been a while. Probably you are not looking at data flow machines. So this question asks for Fibonacci function implementation, right? And it gives you some nodes here that you can use, such as addition and greater than operand, then copy and branch. So you are allowed to use only those, and also you can use constant inputs to feed to your nodes. And that's it. So using those nodes, you will need to implement Fibonacci. So just a quick reminder about Fibonacci. So it is a like series of numbers which goes like 0, 1, 1, and then 2. So basically each number is, except for F0 and F1, each number is the sum of the previous two numbers, right? So basically the next number is 1 plus 2, and the next number is 2 plus 3, and then 8, then 13, and it goes like this. So F0 is 0, and F1 is 1. So this is by definition. And the rest is Fn minus 1 plus F minus 2. And so you can implement this in a recursive manner, but it is, I guess, more difficult in data flow. So just the iterative version is, I guess, easier, where you will just basically do it as I showed here. Start with 0 and 1, and then the next number is the sum of the previous two numbers. So here, in this type of questions, I guess it makes more sense to start simple, like to start with part of the question, but not to like design everything, the entire data flow at once. So you should do it really step by step. So the first step should be, in this question, making the data flow engine work for n equals 0, right? So for n equals 0, your data flow engine should return 0, right? Because this is how F0 is defined. Okay, so let's start with some input n. So I'll write it here. Okay. So we have n. So we'll assume that this is 0, right? But it could be anything. So let's assume this is 0. And so the first thing we'll need to do is to compare this against 0, right? And basically, here we'll try to make this work only for the case where n equals 0. But still, we will need to compare this, right? And then if this is equal to 0, basically what we will do is, so I don't want to connect this directly because we will do something else later. So I will do a copy here in advance because we will copy this n somewhere else. But okay, let's do it like this right now. Okay, so we compare. So we know that here the result will be false because n will be equal to 0, but not larger than 0. And then, so this will generate some flag, right? So let's also copy this flag. And then the next thing we will do is, so if the result here is false, we'll need to return 0, right? And then this is simple. So we'll just basically put here a branch node and then feed this in here. And if this is false, so this is the false path, right? 0 here, which is hard-coded, should be directed to the output, right? And if this is true, you should just consume this, but do nothing, right? So we just consume the 0. And then the rest of the logic will do something else. Okay, so basically, so here, just with this data flow, it is working fine for n equals to 0 case, right? If it's 0, it returns 0. If it's not, if n is not 0, it is not doing anything meaningful. Okay, so the next step is making it work for other values too, right? So for n equals 1, it should return 1. So we should do something else to implement that case. So let me put t here to indicate the true path. Okay, so the next thing we will do is, so since we here check the first iteration, we will need to decrement n if it's larger than 0, right? And then continue iterating. Okay, then we already have the copy node here. So we will copy this to a branch node. And then this branch node will be controlled with the same flag here that was generated previously for n, right? And then basically, if this is false, right, we should do nothing about, with this n which is forwarded here. We should just consume it, but we shouldn't do anything because it's already 0. So the function should be terminated at this point. So the false path in this case is ground. And if it's true, on the other hand, we should subtract 1 from n and do the next iteration. So this is -1. And then basically, we will need to compare this n-1 again against 0, and then see whether it's now equal to 0. So we already have a comparator node here, but so I will do another one. So I'm not sure if this will be possible to reuse this. Even if it's possible to do that, it will be too confusing to understand. So I'll just create a new one because this is hard-coded to this output logic here, right, which is receiving 0. So I'll just duplicate this and basically, so this will be n-1 right here, which is coming. So this is n-1 in this case. So let's copy this again. And then compare this against 0. And then this is basically the new flag, which will be used for all iterations except the first one. right? So for the first iteration, we will use the, yes?
Can you quickly recall how the branch node works? I don't get it there.
Yeah, sure. So branches, so it has two inputs, right? So two inputs should be valid, and it outputs either from the false path or true path, right? And basically, so one of the inputs is the flag, and one of the inputs is data. So if flag is true, the data goes to the true path. If flag is false, data goes to the false path. So the token is generated only on one of the output paths in the branch node. Is it clear? Okay. Okay, so we do this. And then now we'll build our, like this addition operation here, which adds together the last two numbers in the sequence. So for that, we will need another control node here, another branch node, which will be again controlled by the same flag. So from now on, we'll always use the same flag. But okay, so we'll also have some adder node here. And for n equals 1 case, we'll just need to add together 0 and 1, right? So we know that. So for now, let's just hardcode those values. So I will draw an 0 like this, and we can also draw 1 like this. Is there anything we're missing? Okay, so I don't think so. So you can ignore this branch for now. We will connect this later. So let's just consider n equals 1 case right now. And basically, this result should be forwarded to out if branch, so we have another branch here, this is data, and this is control that's getting. This is the true path, this is the false path. And this false path, sorry, it's kind of ugly, but this false path should be connected here to the out in this case. So basically here what happens is, in the first iteration, if this flag here, if this comparison results in false, the output will be produced from here, right? And then the rest of the Dataflow engine will not be active because it won't have any tokens here. So I'll show you a quick example of how it works with some random n number. But when in the first iteration, this comparison generates true, then we won't be using this output logic anymore, right? So the output will come from here. So for example, for n equals 1 case, this will generate this will generate true, right? And then this value will just be consumed, and then this true will go here, and then this will cause n-1 to be generated, right? If this was false, n-1 will not have been generated because it's grounded here. Okay, n-1 is generated, and then it's forwarded here, right? And this is basically the sum of 1 and 0, which is forwarded to the out. Okay, so I think now we have it working for the two cases, 0 and 1, which were the like hard-coded values for Fibonacci sequence. And now we'll just make it like work with any arbitrary n. And for that, basically, we'll create a loop where this result is forwarded on the true path back to this addition logic, right? And then this is basically, so this will need to be connected here. But we'll need to forward the same value to this branch logic 2, because this will be the n-2, if you will, right? So this data forwarded here is just the result of the previous iteration, n-1, but we will also need n-2, right? And then we will get it from here. Basically, we will forward this value here and then copy it. So I will put a copy here. And then this copy is copying the value here and also here to this branch logic. And this branch node is, so this is the false path, and then this is true path, which generates value for other iterations. So this hard-coded 0 will apply only once in the first iteration. Okay, so this is kind of ugly, but here we have copy node, and then this gets 1 in the first iteration, and otherwise gets a token from here, from this pad. Okay, so is there anything that we are missing? One thing we are missing is this, so we haven't connected this here, which is like continuously generates n-1, n-1 for each iteration. So this should go here as the data input of this branch. And I think we have all other paths handled. Okay, so let's test the case where n equals 2. How much time do we have? Okay. So I hope I'll finish like in 5 minutes. Okay, so let's just test the n equals to 2 case. I think we already verified n equals to 0 and 1. It should be obvious here. Okay, so for n equals 2, so we start from here, right? So this is the only place where we have a token ready to execute, right? So this is n, which is 2. We know this is 2. And then, so this is being consumed by this copy node, right? So I'll just show it like this. So this is also forwarded here. So we have 2 on those 2 places. And then this node is also ready to fire because it has all its inputs ready. So we have here streams of zeros, and then here we have 2. And then this node will consume this 2 and will generate true, right? Because 2 is greater than 0. And then this node is also ready to fire, and then we will copy true here, and then we will also copy true here. Okay, so we have the flag here, t. We have data 0. So this node is also ready. So we will consume t here, and also this stream of zeros. And then since this is true, this will do nothing, right? Because it's connected to ground. So basically, this thing will like terminate here and will not be used for the rest of the iterations. Okay, and now what happens is, what else we have ready here? How
come that branch in the top left has 3 inputs?
This one? Yes, it shouldn't have 3 inputs. So basically here what I tried to show is those 2 data inputs are connected to each other, right? So it's just a shortcut. So basically a token either comes from this path, from this copy node, right? Or from this copy node. So in this case, for the first iteration, it comes from this copy node, right? So we have 2 as data here. We have true as a flag here. So we can also consume those 2 values over here. And then when this branch node fires, it will forward 2 here on this path, right? And then we have 2 and -1. This is also ready to fire, and this will calculate 1. So we get 1 here. And then we copy 1 here, and then we copy 1 here, right? So this time, we receive data from this path. And this pad is not producing anything anymore. Okay, and then we consume this 1. This again generates true. And then we copy this true here. We copy true here, right? So initially we had 0 and 1 here for this addition. So we consume those 2. This is 1. The result is 1. And then this branch node is ready. We consume those 2, and from the true path, we get 1 here. So this was copy node, and then copy node copies 1 here, and then copies 1 here, right? And then this branch is ready, so we consume the true and 1, and forward 1 from the true path So this addition in the next iteration, the current iteration, gets 1 and 1, right? So previously it was 0 and 1. So it's 1 and 1, and then this is being consumed. We get 2 here. Okay, so actually we found our answer, but this is not directed to the output yet, right? Because we don't have the flag ready here yet. So we need to propagate the flag. So yeah, I guess we forgot that path. So here, this flag should also be connected here, right? So it's same as the data. So as data receives the token from like 2 different paths, so the flag is doing, right? So here the flag was true. So we get that true here, right? And then this true is being consumed. So basically 1 is forwarded here. And then 1 minus 1 is 0, right? And then 0 gets here. And then it gets copied here. And also gets copied here. So this time, this comparison node generates false instead of true, right? And then this false is copied here and also here. Sorry, this is false, right? And then since this is false, this is grounded and it's not generating any more tokens here on this pad, right? And then we have false here, and then this false is forwarded here, right? Which is again grounded. So this just consumes this with whatever data is here. And then we also copy this false here. And we had 2 as a data here, right? And this is the false pad. So we basically forward this 2 here to the output. And we get 2 for a case where n is 2. So this data flow may not be like very obvious at first, but basically you need to iterate yourself with different values and maybe try different implementations. But the main thing that you need to get from here is that concept of producer and consumer, right? So a token can only fire, a node can only fire if all of its input tokens are ready. Otherwise, it cannot fire. Yes?
On the top left, we have the regular that node. We connect the output to the data into the branch, to the tag.
Here, you mean?
Yes.
This part? Okay, yeah, so this is the flag part, right? Oh, no. Okay, yeah, okay. I guess you're right. So this basically should be connected here. Is that what you're saying?
Yeah.
Okay, yeah. Okay, I guess other questions? Okay, then we can move to, question?
So the concept correctly, so the inputs like 0 and 1,
Mm-hmm.
they can only use 1. Or like how do I decide which to use
Yeah, I mean, so here in this notation, it's not clear, but so you can do that in a data flow engine. You can define to have like constant stream of some value, right? So here, I think I explained like that. So here we have streams of zeros. So I will show it like the 0 ... So it continuously gets 0 tokens from this input, right? But those are just one-time values that are being generated only once when you initialize your data flow engine. So same here, this is also ... And same here, -1. Okay, so those are all streams, but those are initial values, this 0 and this 1. So this is also stream. I guess we need to make the notation more clear. Okay. Okay, I think we'll continue with other questions.
Okay. So the second question is from homework 4, the pipelining question. So here in this question, we have 6 instructions given to us, and we need to calculate how many cycles do they take for different configurations of the hardware. So we have some information here that we are going to use in each bullet points. So the first question asks, how many cycles does it take if we have a non-pipelined machine? So here, So first of all, if you don't see very clear explanations in the exam, you can put your assumptions as it's stated in this note 2. Sorry, not somewhere. Yeah, note 2. So as long as you make assumptions that make sense and you follow, you be consistent across the question, then your solution should be fine. And here we make an assumption here in the first question. So in this part, we see that when we have a pipeline, fetch takes 1 cycle, decode takes 1 cycle, execute takes 6 cycles for multiply and 4 cycles for addition, and then write back takes 1 cycle, right? So our basic assumption here is when we run a mul, then it's going to take 9 cycles. When we run add, then it's going to take 7 cycles. So in total, it's going to be 48 cycles when you just add them up on top of each other because we don't have pipelining here. In the second question, we have some configuration for some pipelining. So we are using this scoreboarding technique. And in our hardware, we have 5 adders and 5 multipliers. And we do not have any data forwarding, right? Okay, so one thing we need to be very careful about is the data dependencies here. So if you look at these registers, as noted in this note 1, each instruction is specified with the destination register first. Then this line means you multiply R1 and R2, and you write the result to R3, right? And in the second instruction, you need the value of the R3. So the second instruction has to wait for the first instruction to complete and write back the results to the register file. So I can just actually mark this data dependency here. As you can see, the mul gets into here, fetch, decode, and then it has 6 cycles of execution and then writes back. And when you have the second instruction, you fetch it, and then you need to wait until the result of R3 is written back to the register file to be able to successfully finish decode. So we have this kind of dependency here. After write back, we decode and then continue, right? And then you just follow the same idea for the other instructions as well. So I just put like 2 rows here because it doesn't fit, the whole thing doesn't fit into one line. So this is until like 16th cycle, and I repeated 15 and 16 cycle here. This is just copies of these. And then you can follow the rest here. So another dependency we see is between these instructions R7 result and this uses R7, right? So this has to wait for this, and it is the same thing. We write back and then decode here. And when we look at the multiply in the last instruction, so it uses R5 and R6, and these are calculated by these instructions, right? So these instructions complete in 15th and 16th cycles. So we already have the data in the register file when we come to this decode stage. Then we don't have to stall, and we can just finish executing the program in 28 cycles. Yes?
Why can't you decode the following instruction while it is executing?
While executing?
Why can't I decode the second instruction that is dependent?
So this decode goes to where in your question? Ninth? Third column here? But you need to finish the execution to understand what is the value of R3. To be able to get the R3 and put it to the... Yeah, but in the decode, you read from the register file, right? So you fetch, meaning that you fetch the instruction from instruction cache, and then in the decode, you read the...
So fetch the operands is in the decode stage, like include.
Yeah, so you need to fetch the operands from register file and decode stage, yes. Okay, so in the third part of the question, we have one simple difference here, which is we have data forwarding now. And we still have 5 adders and 5 multipliers here, and we are using scoreboarding technique. Okay, so what matters here is now we can get the result earlier than we were doing in the previous part, right? So the result of the first instruction is ready here at the end of 8th cycle, right? And then we don't have to wait for it to be written into the register file, and then we read it from there, right? So in this case, we have a data forwarding. So I just assume that this data forwarding happens from the end of the multiplier or adder to the decode stage, which gives me this kind of dependency here. So I can say 1 cycle here. So this decode was in 10th cycle, now it's in 9th cycle. And you continue and do the same thing, and then you see that at the end, you just save 2 cycles here. In the third part, now we have a little bit more change. So this is like the first case. We do not have data forwarding, but this time we have 1 adder and 1 multiplier instead of 5 of them. So here actually another assumption comes. Here we assume that once we start using an adder for an instruction, then we cannot pipeline inside this adder. So we just give the inputs to this adder, and we get the output at the end of the 4th cycle. Or in multiplier case, it's at the end of the 6th cycle. So here, what matters is, so this part is, this R3 is exactly as in the B part of the question. But when we have the second add here, then we cannot start executing here because at this cycle, the adder is being used by the second instruction. So we need to wait until it's completed, and then we start using it from this side. And then once you just follow the same idea and do the rest, then you see that now we completed 31st cycle, which means that in the previous one it was 28. Now we have lost 3 cycles because we don't have additional adders and multipliers. And the last question is, if you do not have, do you have a question? Okay. So the last part, the same story. We have scoreboarding, 1 adder, 1 multiplier with data forwarding. So what we do is basically we just copy paste the result in the D, and we just push the cycles back based on this data forwarding, which is the same thing we did in the question part C. So this is like a bonus here, like 3 points, right? Because it's just some redundant thing. And if you complete it, you will see that it's going to complete in 29th cycle. And that's all of the pipelining question. If you have questions, I can answer. Yes? I think, yeah. So I'm not sure if it's very realistic, but it can be okay. I'm not sure. Could you email after the class, and I can give you a more deterministic answer? Yeah. Yes.
Go back to the example.
Which one? This one?
In line where C is stored, where does the multiple unit become just stored?
this multiply unit. So this is, okay, so there's another bottleneck here, right? So you have to fetch and decode these instructions, and you have a bottleneck over there. So the fetch stage of the pipeline is busy with the second instruction still here. So you cannot fetch this. So to avoid it, for example, you can go for fetching like multiple instructions at the same time and more complex time. Cycle 11 here. So you're asking why this stalls here? So after fetch, it needs to go to decode, and the decode is busy with this here. Any other? No? Okay. Then we can go for the